Hey Ryan, I think it's 10:01. I think we can get started.
Yep. Yeah, I'd say let's go ahead and get started.
Okay. All right. Welcome everyone. It's 10:02, and we'll get started. Today's webinar is focused on using the calibration assistance tool for local calibration. But first, we have a couple introduction slides, and I want to introduce Ryan Fragapane from AASHTOWare, and he will get us started.
Good morning, everybody, and welcome to the webinar. Thanks for attending. As mentioned, my name is Ryan Fragapane. I'm the Associate Project Manager here at AASHTOW. I specifically work in AASHTOWare with the pavement product. Additionally, we'll have two presenters, both from ARA today. We'll have Wouter Brink, who was just speaking, and we'll also have Harold Von Quintus, who will be here as well. Additionally, this presentation will be available at the medesign.com website. So if you'd like to grab the recording of this, or someone couldn't attend and you want to pass that information along to them, please feel free. On to the next slide there. All right, so just some housekeeping items we like to do on our webinars just to make sure that everyone can clearly hear and the recording is clear. For anyone who may want to watch it post the webinar, please just make sure you keep your phone, or if you're using a microphone on your computer, to keep that muted as well. Any questions you might have today, on the right-hand side of the screen, there's a Q&A box. Please feel free to type any questions you have in the Q&A box. We're going to save questions till the end of the webinar just so we can flow through and make sure we're able to cover everything. But we'll be sure to save about a half hour at the end to address those questions. Additionally, Harold will answer some of the questions while Wouter's speaking. So keep an eye out for those responses as well. So I think that covers pretty much everything on this side.
Okay.
And if we can't get to any questions, just real quickly, we'll respond to them later. They'll be available to everybody. So each year, AASHTOW provides 4 webinars brought to you by ARA. We already did one on December 2nd. That was getting started with local calibration, and that, if it's not available yet, it should be available on the ME Design site. So feel free to go check that out if you haven't seen it. And then we have 2 more coming after this one. One of them will be in February of 21. It's going to be using the back calculation tool and designing for multiple asphalt overlays. And then we're going to have a 4th one before the fiscal year ends. And the task force hasn't decided what that'll be yet. So keep an eye out for those invitations as well. On to the next one.
Yeah, I think that's it.
That covers everything.
Yep. Oh, thanks, Ryan. And we'll open the polls. It's basically the same question as usual. Chad, if you want to open poll 1, please.
All right, looks like responses starting to tail off. Give it about another 15 seconds here. Okay, that closes the poll.
Sounds good. Thanks, Chad. All right. So let's get started. First, I want to go over some of the prerequisites for this webinar. It's as you do need some prior experience using Pavement ME Design. This webinar will not go into using the software, the Pavement ME Design software. Attended webinar 1, getting ready for local calibration. That webinar outlines all the steps needed or items that are required before you can even use the Pavement ME or calibration assistance tool. It goes into detail about knowing your data, understanding what the data shows, what your design practices are within your agency, and to reflect and make decisions based on those items. Then also attended any previous Pavement ME Design, MEPDG webinars that are on the AASHTO or ME Design website. These include anything from enhancements to training and updates and changes to the software. And be familiar with or review the AASHTO guide for local calibration of the MEPDG. That's a AASHTO publication. It is what the calibration assistance tool is based on. So some of the learning outcomes from today's webinar, you'll be able to list the requirements and assumptions for using the calibration assistance tool, identify the steps and procedures for completing a local calibration using the CAT, and identify some of the available features within the calibration tool to guide your decision making and identify which calibration coefficients to adjust based on what your data tells you. Okay, so the main outline for today's webinar is, first I'll go through a brief introduction and kind of review the previous training resources that are available. Then I'll quickly go through some of the calibration assistance tool assumptions and requirements, and then we'll go over to the actual web application and go through a calibration that I've performed using some local data, local pavement sections, and LTPP sites. Okay, let's get started. So to review, last year in 2019, we had 2 webinars related to the calibration assistance tool. The first one was focused on the introduction. It outlined all the requirements, the assumptions, the various limitations, what it was designed for, the guided calibration process that's implemented within the tool, and then a walkthrough was performed to show kind of how to upload the data, start the various calibrations, and run the initial verification. Then the second webinar focused on managing your calibration projects, and the walkthrough was based on reviewing the initial verification results from webinar 1, going through the detailed verification review, optimization procedures, and the validation and data export. So a lot of these items will be covered again today, but with the focus on a specific calibration. Then, as I mentioned, 2 weeks ago, webinar 1 went through the local calibration process and what you need before even using the calibration assistance tool. And today we'll go over a detailed example of using the calibrations tool and how you can use the features within the software to make decisions and guide your decisions for adjusting calibration coefficients. Okay, so one of the main takeaways from the previous webinar is basically you need to know your data. You need to know what you as an agency collect, what you use for design, what you use for materials testing, and ensure that the inputs are compatible between what you have from an agency perspective and what is required by Pavement ME. So we went through some examples in the previous webinar of how some of those differences come about and how to address that. And you also need to base your decisions on what your day-to-day practices are. So if you have, say, multiple databases for a specific input, choose the one that you use on a day-to-day basis. So it's all intertwined together, and to make sure that everything is compatible, which will result in a better calibration. Because if your inputs do not represent what you are experiencing in the field, no amount of calibration is going to be able to fix that. Okay, so next I'll quickly go through some of the assumptions and the requirements, what it does not do. So when AASHTO developed this tool, it needed to incorporate both the MEPDG, manual practice, and the local calibration guide. And many of those steps were incorporated within the tool. So what the overall tool has a 6-part calibration process. It is a mix of automated and manual decision-making steps within each part of the process. So first, this image here kind of illustrates how to go from start to finish. There's the manual steps where you have to make your decisions, which coefficients to change, what your data tells you, which selections, which projects to include, which to not include, which setting up your design matrix, and then making your decisions on standard error, bias, your overall goodness of fit statistics. And then there's the automated process or steps where once you have your projects in the software itself, it will, and you run your project, it'll extract the predicted data, the measured data, and automatically populate the various tables, charts, and do the calculations. So that's the automated step, which is time consuming if you have to do it manually. So from what you need for the calibrations tool, first you need a Pavement ME license. It is available as part of your license. There is a user guide and a user manual, which goes through the different steps in the calibration, plus the screenshots of the various screens within the software itself and what they represent. You will need your measure distress data for the selected projects that you upload, and of course you'll need the DGPX file, which gets uploaded to the calibrations tool and is a representation of your calibration pavement sections. And there's a few requirements that it has to be compatible with either version 2.5.5 or version 2.6 of the software. And this kind of just illustrates all the information that you need to characterize that roadway. So you'll have your traffic inputs that's in each DGPX file. You have your structural layer properties. You have your climate inputs. You have incorporated your field and lab testing, if that is something that you've done. Your measure distress, and then the different construction histories, which can tell you when different fixes or maintenance activities were performed on that roadway. So I do need to mention that there are limitations of the software. It is not a hands-off approach, so it still requires significant user interaction and decisions that are required. It is not a one-click solution, and it does not identify and select your sections, which was covered in the first webinar. So those are the items that are the main assumptions and requirements for using the calibration systems tool. Okay, so now we will move into the calibration tool itself. I'll basically use the software. I will also kind of go back and forth between some slides here and there. I have some supplemental slides to kind of illustrate how some of the coefficients affect the models and how you can use that to make your decisions. And I'll focus on a fatigue and rutting calibration. If you attended last week's webinar or last week's user group meeting, a lot of this information will be repeated. It's going to be very familiar, but it's good to reiterate the different decisions that need to be made and kind of show different examples throughout. I've added a few different runs to kind of illustrate some extreme cases to make sure that these coefficients can be very sensitive to the output and produce very large changes that is not always apparent when changing all of the coefficients at the same time. Okay. And some of the example items I'll go through, I'll go over some of the selected sections, a detailed data review, some of the initial verification items on how you can use those data filters. I'll go through the different optimization runs that I've completed, and then selecting your final coefficients and exporting the results. Okay. We're not doing that yet. We'll do the poll question at the end. And let's go to the calibration tool. Ryan, any questions so far?
Yeah, I was gonna say it seems like we have a break. So we do have two items from Justin.
Okay.
First one was if you could clarify to use the inputs you typically use. And the second question is also from Justin. Shouldn't it be the inputs that are derived from that project?
Let's see. So I think this is when you don't have any inputs currently. So this is more of a setting up and getting ready for calibration, that if you don't have any inputs, that's when you want to make sure that what you select as input for your calibration sections reflect your day-to-day practice. Because otherwise you don't want to build in a systematic bias where for the calibration was done on one set of data that you don't normally use on for your day-to-day practices. So if you use say CBR for your subgrades and now you're trying to the calibration sections use R value or any of these other items, that's building in an extra complexity that from a design aspect you're not going to use. So that's why you want to make sure that everything's compatible and reflect your agency specific practices. And once you input that information into the DGPX file, that is reflected directly. And it's so when I talk about the inputs itself, it's more of a when you don't have your calibration sections ready yet. And all of the inputs that you do have is reflected in the DGPX file, which is then uploaded to the calibration project. I hope that answers. Okay. All right. Well, I think let me. Oh, I don't know what just happened. I do not want to do that. I clicked the button and I don't know. Oh, let me go back to. Okay, sorry about that. Oh, geez. I am sorry. Having some technical difficulties here. Jeez. Trying to remove the bookmarks bar here, but let me close. So it's a little bit better to see. All right, well, let's go. All right. Everybody, Ryan, Chad, you can still see everything?
Yep, looks good.
Okay, great. Sorry about that. Okay, so once you log into the calibration assistance tool, the main home screen, there's a couple different icons here. So you have your upload your ME design projects where you upload your predicted or your DGPX files and your measure data. You can also assign different metadata for certain inputs. You start a new calibration. You have your manage existing calibration projects if you have done those, and then we have the view calibration steps in the help manual. Now it also states here, Pavement ME, the calibration assistance tool is compatible with version 2.5.5 and version 2.6 of the software. So if you have projects for V255, you can upload them directly. And if you want to use V26, you can do the same thing. I just want to go over a few things here on the uploading your projects. So once you have your projects uploaded, all of them will be displayed within this window. So I have about 23 uploaded. They're generic projects. Most of these are new asphalt, new AC designs. And you can see the version that I've uploaded them for. And I've uploaded the measure data as well. And when you do have measure data for a particular project, it'll state that it is available. And you can also see when it was last updated from a project's perspective and when the measure data was last updated. Okay. So I am going to open one of the projects I've already created. So this is the same project that I did last week at the user group to kind of go through the various steps within selecting the calibration and hopefully provide you with a good understanding of what is needed. So first, I have selected all of my owned projects. So all the projects that you saw in the previous screen for manage your pavement sections will show up in this list. Now, if you do not want to select all of them, you can deselect certain ones if you have multiple different distresses that you want to, or multiple design types. So if you have a mix of rehab versus new, a mix of PCC and AC sections, then you can select the ones that you want to include. But for here, I'm going to select all the projects because that's what I've selected for this. Now you want to say which design types and distress types you want to calibrate. So the options are basically your new AC, you have your new semi-rigid AC rehab, and also new JPCP, CRCP, JPCP rehab, CRCP rehab, and short jointed plain concrete pavement. And within each one of these, you'll have your different distress types that you want to calibrate. So for this example, I've selected both bottom-up fatigue cracking and total rutting. And once I've selected this radio button or slider, now it pops up the information that you will want to use to generate and populate your experimental design matrix. So for these, I've selected basically the same, all three thickness levels. So less than equal to 5 and greater than equal to 10 or greater than 10. And if you only want to say you want to do a calibration where you know you only want to see how the models are impacted with thick pavements, you can select a specific one. For this, I've kind of kept most of these unchecked, which will still, it won't filter the projects based on those values. And for my traffic levels, I've kind of set the limits for low and high traffic. Then for total rutting, it's very similar. I actually kept the same selections for the experimental design matrix, and these should typically reflect what you see on in your roadways or in your agency or region. Okay, so once I've selected this, I click proceed, and it'll take me to the define your minimum number of sections. And this is to guide you to see if you have a number of sections that you can use from a to make statistically sound conclusions based on your standard error, your bias, your hypothesis test results, and it gives you an idea of what is my tolerable bias, and tolerable bias would be the average measure versus predicted, and that difference. So for bottom of fatigue cracking, we have everything's in percent lane area, and that would be 2.5%. For the default value, you can change these as you want, and the standard deviation of the maximum distress. How variable is your distress data from a project to project standpoint? So if we ended up, say our standard deviation is 10, it'll increase the number of sections that are needed to make statistically sound conclusions. And say if we change our tolerable bias to, say we only want to have 1% bias, then it increases it significantly. And the same thing can be done here for rutting. It's a way to guide you into identifying how many projects you should or want to have. And it does not actually limit you from having less projects. It's there to kind of tell you, like, yes, you probably need more based on what you based on the exact information that you have from your measured distresses. And then you click on proceed and go to the review distress data. So the calibration tool will look at your maximum distress for all the different sections that you have measured data for, and what you have selected in your first step. And then it'll produce a distribution of where does your distresses lie from a maximum standpoint. And I use this to really see if all of my distresses are within certain categories. Does it capture the full trend of predictions over time? And do I have enough magnitude to actually show what is expected from a prediction standpoint? And you want to be able to capture early age cracking, distress, rutting, plus basically the next stage, and then also late age. What kind of performance do you see at the end of the service life? And it provides you with the mean values, the median, standard deviation, and your number of sections. So here, standard deviation for rutting is 0.18. I can go back to define your minimum number of sections, and basically your tolerable bias or your maximum error is 0.18. Tolerable bias, I want to have basically for rutting, it's fairly low. Let's say 0.1. So you need a lot of sections for that. So if you say 0.1 as the tolerable bias, you only need 9 sections to make statistical conclusions, but it's still recommended to have more. The local calibration guide goes into more detail as well on recommended number of sections for each distress type. The other part of this plot is to show you what's your age of your different projects. What is your distribution? So are all your projects with less than 5 to 10 years? That can impact your calibration coefficients, because if you have a lot of this early age distress, you're going to calibrate to that. And if it's a young or early on in its life, then you might include a bias for those projects that you try to design for 15 to 20. So if you're designing for even 30 years and you only have projects that are less than 10 years old in your calibration set, that's not truly representative of what your design practices are. And you need to either build your projects as you go or select other items that have or other projects that have a greater distribution in age. And as you can see here, we have 23 sections and then the other information. So for bottom-up fatigue cracking, it'll produce the similar charts or histograms to show where your distresses lie, and similar for age. Okay. Now, once you go to the final selection review, it'll populate your different projects within the criteria that you've selected for your experimental design matrix. So as you can see here, there's a project that reflects less than 300 AADT. You have a thickness less than 5 inches, and it's less than kind of low precipitation or lower precipitation. Its mean annual air temperature is less than 5, and it is a coarse grained soil. So you can see here we have 2 projects here. We actually have a ton of projects that are represented with within this cell, which ultimately you want to distribute them equally amongst all of the different cells. So you might go back and change your your experimental matrix criteria to kind of distribute these amongst other cells to try and have an equal amount in each cell. And these sometimes it just depends on what you're constructing or what you have available, and you can make decisions based on that. And you don't want these sections to control or create a bias specifically. And we can look at these in the detailed review. And it'll populate for all the stress types that you've selected. So you can see the fatigue cracking one might be slightly different, or they might be the same depending on what you've selected in the previous step. Okay. 1, 2. So now we'll create the initial verification. You select the different coefficients that you want to use. Do you want to use the global model coefficients that are reflective here, or you can import previous local calibration coefficients, assuming that they are compatible with the version that you are using. And one way to do that is you can export or save the calibration coefficients that are from Pavement ME and then import that file. I do want to mention a few other things. I looked at, after running these files, so you can see here they're complete. I didn't change anything. They've run, all of them ran to completion, and then it opens up the data analysis interpretation. So within this screen, now you can do a detailed review of your different sections, plus have these filter criteria to kind of help you make decisions on what do I want to use and what do I want to change. So one thing I'm going to do here, overall, the model bias is very low for running -0.01 inches, which is within that tolerable bias. We have a SEE of 0.17, which is fairly low, but you can see there is quite a bit of dispersion within your measured data. And some of the trends here for your predicted versus measured, you can kind of see where the bias increases as your values, basically your bias increases with the measure value. So it's you can make decision on your predicted distress and how you want to adjust the models, or if this section is very different from all the others, why is it performing that way? So it allows you to ask questions and further review your different information. Now, so say if I want to only look at thin pavement, so less than 5 inches, I can select that and update the filter. So you can say, okay, well, this is a very thin section. So what can I draw from this? So why is it performing that way? Are there specific items from a forensic investigation that explains why it is performing that way? Is there a design criteria that or input that we didn't account for properly? Is there subgrade issues? Is it all subgrade based rutting? Why is it performing the way it is? And sometimes that becomes a little bit more clear when you look at cores or dive a little deeper into what that section represents. And if you scroll down here, it also shows you your measure versus predicted from a time series standpoint. And you can see here, project 3 has a lot of rutting, while the predicted is almost nothing. So how can you change the models to account for that? Or if it is an outlier, do you need to remove that section to avoid skewing your results? Okay, let's see, we can do other ones here. Well, we'll keep that. Let's see if there's a difference between fine grained and coarse grained. So, okay, so that section is a fine grained section. So as you see here, there's one, but why is it performing differently than the other section within that? And that's kind of how you can use these different filters. It's a pretty, I like using it just to guide me into selecting various coefficients. From a fatigue standpoint, we can go look at some of these examples as well. So you see here, okay, well, this project performs much different than any of the other ones selected in your set. So what is different between that one? So let's go try and go to thickness greater than 10. So it's not that one. It's okay. So we'll have to adjust the calibration coefficient slightly. Thickness between. So as you can see now, there's that section. So it's between 5 and 10 inches. And now you can further investigate why that's happening. And I've kind of done that where I went back and looked at cores for these sections and kind of found from these cores that this is actually top-down cracking. So we are going to exclude that section because of what the cores show us. And that's where doing some forensic investigation on your sections is so critically important to verify what you're seeing from your measure standpoints and to verify your different thicknesses, because as design thickness may not be representative of what you are seeing, what was actually built. So that's why we've always suggest using at least some forensic investigations, just cores at cracks, even the wheel paths. You can tell if there's basic debonding between the different layers. If there is, you can kind of look at the different interface friction values that you can input in Pavement ME and try and represent that in a as close as possible to what you're seeing in the field so that the software can account for those different issues. It will not account necessarily for any material related issues like stripping or moisture issues, or if the base is basically saturated, and then you'll have to decide how to approach those different projects. And is there a difference, say, between the wheel path versus non-wheel path cores? Okay. And that's kind of why, in the end, I ended up removing this section because it was top-down cracking. That's what the core showed. And we don't want to use that section as for bottom-up fatigue cracking because it's not representative. And it will bias your results. Let's see here. Other items, you can look at traffic as well. And you can also see if the bias increases with time or not. And I've actually done a quick look here where I summarized kind of different bias and SEE values for the fatigue cracking example. And I use this to kind of see if specific groups have significantly different bias statistics and standard error. So you can see here that thickness greater than 10 inches for some had a lot higher bias. So for this, it underpredicts, the models underpredict, and there's a big difference. There's not too much of a difference between thickness less than 5 and 5 and 10. Then for coarse grain subgrade, there's a slight difference between coarse and fine. And then your traffic levels here, greater than 2,000, there's a difference between the different traffic levels. And these are all values that I took directly from the software itself. And then you also have your hypothesis test, so you can look at those to see if you actually need calibration. Okay. Let's go back to clearing all these filters. I think, which one do I have?
While you clear those, would you want to answer some questions? We have a few questions that have come through. Or
Sure, I can try.
all right. So I think the first one we have here is, can the calibration assistance tool calibrate rutting and rutting in AC, excuse me, and subgrade separately? Right. They added a follow up there just saying that they have AC and subgrade rutting measurements separately at their agency.
The tool does not, because most agencies and most people do not have that information. And it's really only obtained through trenching of your different projects to see what that contribution is. The tool only looks at total rutting. So you can change the base and subgrade rutting coefficients independently, yes, but it's not going to say do AC by itself. We have implemented some guided procedures for that, where you can look at some very thick or thicker AC sections. You expect that the rutting will most likely be in the AC layers only. So you could derive your AC coefficients using those thicker sections and then adjust the bias, or then apply those coefficients to the thinner sections where it is kind of expected that base and subgrade rutting will have a larger impact compared to the asphalt. So there's a process like that, but that's something to consider. But it depends on if you have that information available, and how do you verify that that is actually in the field. And if you have done a lot of trenching, then you have that information. But it can be reflected in how you choose your coefficients.
All right. We have another one here. You let me know when you want to stop answering questions and get back to it. So
Okay.
but we can do maybe a few more. This question came about 10 minutes ago and says, "Are these max values?" Then they followed that up with, "Is your trend, if your trend is variable, can the max can be earlier in life?"
Yes, it can be, but from a reviewing your initial review is just to make decisions on why, to see if you have enough distress values or magnitude to calibrate to. Yes, your individual measured distresses will vary over time, and you might have an increase, decrease, as you can see with some of these variability within these projects. But the max age and max distress distribution is just to determine that you don't calibrate to only having projects less than 5 years, or if you calibrate to everything with less than 5% cracking. Yes, you can calibrate to that, but is that going to be useful for those pavement sections that do not exhibit that? So what you use in calibration still needs to reflect your agency design practices. And you can build in a bias or limit your inference space if you don't take into account the overall maximum observed values. And within time series data, these are the actual values. These are not max values. These are what was observed and measured in the field. So for you're calibrating to the actual measured performance, not the max values.
All right. And we have another one here that says, what are your recommended value of tolerance bias for each type of distress for AC pavements?
I would kind of follow what the manual practice does show. There's a kind of there is some recommendations in the guide itself, and you can try and compare it to the global models itself. So it depends on what you see in the field, and really what you're going to see here as an example too is the bias in the SEE for the global model doesn't necessarily show that it's a good fit. And then when you start changing and reducing bias, your standard error might increase. You want to get it as close as possible from a calibration standpoint to zero, to have it to not have a consistent under or over prediction in your results.
I think we're almost through all the questions, so we'll just keep moving through them here. I think we should be able to get them all wrapped up.
Okay.
This one's about early age predictions. It says,
Okay.
"Seen some inaccuracy at early age ME predictions, as was expressed by other agencies last week. That said, would you recommend removing sections data that's less than some age? Question mark. If so, anything less than maybe 5 or 10 years?"
I know the manual practice and the calibration guide recommends having at least more than 5 to 10 years, just so that it can account for later age distresses. And it all depends on what you have available. And you want to have at least 3 to 5 measurement points throughout. So if you're only collecting data every other year, that's 6 years right there, if you only want 3. And it depends on how you collect that information and how it compares to other similar sections, right? So one thing we do in here is too is that's kind of where the experimental design matrix come into play to see if a specific cell performs significantly different, or a particular project performs different than every other project within that cell. So it's kind of, you make those judgment decisions, and yes, I mean, you don't want to calibrate to something that prematurely failed that's not really accounted for in pavement ME. So if it's a moisture related issue or a construction related issue, pavement ME is not going to be able to account for that. So you need to know your data and what sections you have available to make those decisions. So it's all made up front before you even get to the calibration tool.
Thank you. So we have another one here. It says, in the select initial calibration coefficient slide, can you explain the process of calibrating the IRI as it uses locally calibrated coefficients? How to import the calibrated coefficients from other distresses?
Yeah, so how this would be done, IRI is kind of a separate case, and I've always done it last. So I'll go through, calibrate my running coefficients, cracking coefficients, everything, and then I'll go import or combine all the different coefficients in Pavement ME and then export that. And then use that exported results and import it as your local coefficients, because then it applies your local AC routing, base, subgrade, and everything, and all the different calibration coefficients to adjust your, and then you can focus on the IRI itself. And I think a feature that we might be able to add at some point is where you can, if you select, instead of import, you can enter the coefficient that you want to run for each specific calibration values. Okay.
All right. So just a few more here. Where did you input the measured distress data?
Okay,
So
so
the data format be?
yeah, so the measured data, as I mentioned in the beginning, is when you upload pavement and design projects, that's where you import your measure data. So first, I typically upload you need to upload your DGPX projects first. So you have your project file name, and that uploads to DGPX. And then down here is your measure data upload. So you have your measure data description. So it kind of gives you a description of the units of those inputs, what they need to look like. You can also download a measure data sample format, plus you're download an empty measure data sample format where you can include your specific sections. But the main thing you want to ensure is that the project name. So if you have a section ID, I can actually, let me download this, kind of show you. Now this is just an example, and basically is your ID, your H month, fatigue bottom up, fatigue top down. You have your all the different distresses, and then you have the actual name of the project, your age, and then your fatigue cracking or whatever. Now you can have these mingle or interchange together as long as they have the correct column and the name ID matches exactly what your project upload ID is. So that's how it matches between the predicted and measured data, is based on that initial ID name. So you have to ensure that that is the same. And the calibration tool does only uploads and matches the information from these measure data files. Okay.
All right, and we just got a few more here. Can we manually input coefficient values?
Not currently. There's no manual way to enter them other than going through the calibration process itself, where you can change and adjust them. But no, and that's what I kind of mentioned, that might be a future feature request to kind of set your initial and manually update the coefficients. But typically it's easier just to import the different coefficients.
Okay, and then we have, it says, so this is kind of continuing on with the question that was in the select initial calibration coefficient slide about IRIs. So they said in here, the CVS file of the coefficients will be uploaded, and then the verification process will be run, and then IRI calibration coefficient will be calibrated. Is that correct?
Yeah, and it is not a CSV file. The local calibration coefficients that you import is the XML that can be exported from Pavement ME Design. And to show how that can be done, so you have your software, you have your ME Design calibration factors. You can actually click on export and should do it, but it's typically more when you have a project already open, right? So let's say new AC, flexible, go to your sections here. I think yeah, you can select on project, and then there's import calibration settings and export calibration settings. So you can basically adjust them in the software as you need, and then export them directly, and then upload that to the calibration tool. I know that was pretty quick, but that's one way to get your imported files.
Looks like we have one more question and then we can get back to it here. There are standard deviation equations associated with each type of distress. These are listed along with the calibration factors. Can you please explain how they are developed and involved in the program?
Yes, I'll get to that
They're
at the end.
different. Perfect. All right, go ahead, Wooder. You got covered.
Okay. Okay. So now once we've done all the detailed review, we've basically removed certain sections that were known to be an outlier or top-down cracking. Now we can go to the next step, which is optimizing and start optimizing and adjusting the calibration coefficients to reduce your bias, eliminate your bias, and reduce your standard error if possible. And just to summarize here, basically for this example, we basically have observed a underprediction of your fatigue cracking compared to your measured distresses. Sections with greater than 10 inches have a larger bias compared to some of the other ones. And calibration is required based on your hypothesis test results. Okay, so now we move to optimization. I'm going to focus on the bottom of fatigue cracking because I think I have a pretty good examples here. So as you can see, now our bias in SEE is slightly different. So why is that? So if you click on the view, when you have more than a certain amount of sections, the calibration tool will automatically split your data set into optimization, a set for optimization, and then a set for verification. So here it already split that. Now it just shows you the data available for optimization. It doesn't show directly with your initial verification, but if you click on, if you've run a specific optimization, now it'll show you your optimization set and your validation summary. And that's based on a random split sample as recommended in the MEPDG local calibration guide. So now that we have this initial verification, where do we go? How do we use this data to improve the calibration factors and reduce your limited bias and reduce your standard error? So as you can see, we have 190 points. Our slope is 0 because most of our data is here. We have a lot of measured data, but not a lot of predicted. Our intercept is 0, which it just fits a linear regression line through all your data points, which happens to go, it's not statistically different than 0. And your pairwise difference here is also 0, so it is statistically different than 0. So I have a couple items here. So what we need to do is we need to increase the predicted cracking to reduce the bias and reduce your standard error. So how do we increase that? And how can we use the model form and inputs to make those decisions? So for cracking transfer function, that's typically where I start. You adjust your C1 and C2 coefficients. Damage function is your BF1, BF2, BF3. But I typically try to look at the transfer function first and then decide on the damage function, because that has a much bigger impact on your actual predictions. So for the transfer function, basically your C1, it will shift your initial cracking where it starts propagating based on the predicted damage. So you can see here, if you change your C1 from 0.25 to 2, it'll shift it along the curve here. And I have different thicknesses in here, but they're pretty much the same. There's slight modifications or slight deviations between them. And then you have your C2 coefficient, which adjusts the rate of cracking. So you can see here where it adjusts that slope and how quickly it'll crack through, or basically the slope and rate of the crack accumulation, while holding basically the C1 values constant between the different items. Okay, and then in 2018, the transfer function for C2 coefficient is actually dependent on thickness. You can still calibrate using a constant value for all the different thickness levels, but from our global calibration, we saw that sections with less than 5 inches kind of performed similarly, had the same coefficient, and once you get to 5 through 12, there was an increase in the C2 value based on the observed data. Now, and then for thicker sections, it was also pretty much constant. So how you can use this information is to adjust your coefficients, either by changing the endpoints here. So if you see a lot more or less cracking with your thin sections, you can lower this part of the curve slightly down. The software will automatically increase the slope of this line. And if you do see that you want to change the thicker sections, you can actually shift that up and down as well. So if you change any of these endpoints, it'll readjust the slope accordingly. You can also overwrite that and just have a constant value for all items. And for the fatigue damage function itself, you can kind of see here's it adjusts your total number of load repetitions for failure, and basically BF1 increases or decreases that NF, and similarly for BF2 and BF3, it adjusts the slope. And BF2 is related to your strain, which you can use to modify certain coefficients if you see that, say, your load will impact your different strain levels, so you can adjust the load coefficient. And then for your modulus here, you know that mean annual air temperature modulus is dependent on your temperature, so you can adjust those as well if that's what you see in your data. And really, which ones you change depends on what your bias is telling you, using your different filters from the detailed review, and also using the analysis of variance table that is down below here. So I typically start with, since all my binder types are the same, they're all, most all, subgrade type I'm going to take out for now, and data source, because yes, there are LTPP sections included in this, but they are kind of uploaded as local segments. So now I want to focus for fatigue cracking on your AC thickness, your mean annual air temperature, and traffic. And then we see if there's a significant bias within any of these. And currently there's not, but that's not necessarily expected because our predictions are so low. So the first run I did, I made an incorrect one here. I clicked run optimization before I actually changed anything. So I'm skipping that one. And so for this one, I adjusted I put in a new value for C1. I adjusted it from 0.25 to 2 in 5 increments and ran the analysis. So based on that, where is it? Now you can see here's my 5 increments that I ran. You can see the bias and SEE for each one. See if where crosses 0. So maybe for C1, for a bias of 0 is somewhere between set 1 and 2. And if I click on each one of these, it will update the plots and figures with your new bias, SE values, and so on, and give you new hypothesis tests. So for this, I have a C1 value of 0.25. So I basically shifted that curve, shifted the C1 curve all the way to the left. And I've kind of an example here of some of these where you kind of see here's my damage plus your C1, the different coefficients and how those S-shaped curve are affected based on different C1 and C2 values. And then you can kind of determine which one is best. And that's just to illustrate how some of these items are calculated. So as you can see, for a C1 of 0.25, now I have a lot more sections that overpredict my measured rutting, even though all of my hypothesis tests are passing. So there's not a statistical difference between the measured versus predicted. There's also no statistical difference between the intercept of 0. So when you plot a linear regression line through here, it's basically going to be right along the line of equality. Now, is this acceptable where some of these sections are over predicting so much? That is up to you to make that decision. And then you can go through and see which ones here I have So I would say this one is better. The slope is still significantly different than 1. You have here, it's another example where it kind of moves some of them, increase some of them, and kind of then you make a decision on which ones you want to use. I would not go for that one. And I ended up selecting this version here, but I would question what is going on with this section and why it's happening. So you can still refine if you find some differences later on, you can go back to your detailed review and restart. But knowing that if you are in your detailed review and you select update projects, it's going to change and remove all of the optimization runs you've already completed. And just to kind of show, this is running back up to fatigue. So you can see I ran quite a few here. So look at this, and then you can use, now we see for this particular one, there are some significant variables, and we'll remove some of these again. And this is kind of to illustrate how interactive and how you have to make decisions as you go. It's not going to just give you a final optimized result, because many of these coefficients really have a physical meaning and need to be able to represent what you're showing, what's seen in the field with how the models are being used to predict. So now I can go through some of these, and I've accepted this final one where I changed different, I'll show you this one actually, where I have 36 different combinations that I'm running, and I have 21 projects, so that's 750 runs, and it ran in probably 5 hours. So that's pretty, just gives you an idea of how long it can take depending on how many runs you have. If you're changing all the coefficients with 10 different levels each, your analysis is going to take a long time. But what I wanted to show here is I've changed, I think, quite a few different ones. So I've changed C1 and the C2 constant with 6 levels each. So that's why there's 36 runs and 21 projects. So you have your 750 runs. It changed from 0.2 to 1. So you can change these simultaneously, and it will run all of those different combinations you can see here. Typically, I don't do that just because it gets difficult to track and kind of scroll all the way down and up. And from a convenience standpoint, I typically will just select certain ones and run smaller increments, but wider increments, and then refine as I go. So you can see here's your SEE and bias depending on the different coefficient levels. So this one actually has pretty low SEE and bias, so negative 0.48. But there is one that's, which one, where is it? So I select the one with 0.29, which is, or 0.48. So that's selected. You can kind of see what the measure versus predicted looks like. It passes all the hypothesis steps except for the slope. And then you can refine and move on. But here, from a validation standpoint, most of the predictions are right along line equality, except for these couple different sections. So all of these were not included directly in the optimization set. So you go through and adjust these as you need. I'll use the ANOVA table here. If there are any significant variables, say for AC thickness, I think about where would that directly impact the calibration or the model itself. For C2 or the transfer function, that's basically your C1 and C2s. Your mean outer air temperature is more related to your fatigue damage equation because that's a direct, you can relate that to your modulus. Traffic is load. So I would adjust the damage function exponent for the strain because your load will affect your strain. Then I have another example here. Which one is it? I think I used the damage here. Not yet. There is a damage example here somewhere. I think it's this one. Nope, those are still those. Anyways, if you do change some of those damage coefficients, you can have some significant differences in your predictions, where it'll basically go from 0 to 100% cracking for everything almost instantly. I do have for the total rutting. There are some examples of that. I think it's here I changed basically your BR3, BR2. You can see how that is impacted by the different results. There was a nice one. Yeah, so this one kind of show you such variation between these different sections or different coefficients. From a writing standpoint, I think there's one where you can kind of see how the slope here increases every time. And it just depends on what you use for those calibration coefficients. So here's my slope, here's 0.71, but this particular project here affects it significantly. So that's part of the process, is to decide which ones are best based on what your data tells you. For rutting, this one I reduced the bias, got it pretty much to 0. Standard error was pretty much the exact same as the global model, but your bias is less, even though the global model did a pretty good job of already predicting the rutting here. So this is the final, and then you're not always going to be able to pass all the hypothesis tests. That is typical, and you have to make that judgment decision on, is that acceptable based on how your measure and predicted results come out, or knowing that what's different between the sections, should that be removed, and kind of identifying if you need different calibration coefficients for different design types. Okay, so now that I've selected these, I want to see, did I miss anything? Oh yeah, here's a quick example of different BF3 values. So this is for fatigue cracking, where you have your traffic, basically the traffic component, versus the, yeah. You can see here BF3 of 0.6, basically no cracking, BF3 of 0.74, some cracking, then 0.88, which seems like a small change, but then everything, you start getting a lot more predicted fatigue cracking. Okay. So now that I've selected my optimized best judgment on which section or which calibration to accept, here you can see, I mean, the bias reduced from negative 5.32, so you have a significant underprediction, to a slight, very minor overprediction, but it's basically, you're not over or under predicting your results. So I select, that's still the running one. So once I've accepted, I can go to the next screen where now I can compare what it was from before. So here's my global coefficients. Here's my new local prediction value. So a lot of the predictions increase for these sections, while some of these items, some of these sections are slightly over predicted. And here's my verification, that independent set, to see how well those compare. So you can see here bias reduced from -5.3 to 0.29. We have a standard error increased, but I said this is a better calibration or better performance predictions compared to the global. So here everything is basically 0 for your sections. Now, you can question why those measure values are so low. I mean, some of that could include, is there a debond? Is it actually top-down cracking? For these sections, I believe these are mostly top-down cracking based on the ones that I reviewed course, but that's the kind of questions you'd want to ask before accepting your final results, and verify that it's truly bottom up or top down. Now those sections can be used for your top-down cracking calibration. Okay, and then once you've reviewed the summary, then it goes to your formula derivation. This is where you will basically compare your average predicted values for different groupings. So you basically split your predicted data and your standard deviation and residual data into different bins and derive your standard deviation equation for reliability. So that kind of answers the question from the user or the attendee about deriving these items. But you should also be careful to make sure that these values, so this is fitting a model to the data itself, but that is looking at a complete, just using numerical methods for it. And you need to check that you do have typically what we see as basically at your 0 minimal predicted values. You should have basically almost no bias. And then as you increase in age, your predicted values increase and your standard deviation of your results may also increase. So this captures the variability within different groupings along your sections. So this standard deviation is intended to really account for the variability within your measured and measured data and your difference between the measured and the predicted. So this will have an equation, and for rutting, it is a power function. But one thing I'd want to check, you always want to check the form of this. So as you can see, the global model has a power function. And for this example here, we actually have a negative slope in your power model, which is not, yes, the data and the fit optimized to that value, but that's not how that is typically modeled. And I can kind of show, and that's some of the items you want to check when you go through this process. Kind of, you want something similar to this where as you go further along, I mean, if it's a constant value, that's good. And it just shows, like here, I would interpret this as my predicted running increase, the bias decreases, but it still, you do not, it'll affect your reliability equation as you, because it's based on the predicted rut. So here your rutting value, and it should be a representation of your dispersion within your measured data and your residuals. So here I would say for predictions, you have more error between 0.1 and 0.2 prediction rutting from measure standpoint versus when you have the higher predictions. And that kind of comes across in some of your measure versus predicted plot as well. So these values are much closer, and then a lot more dispersion between your measured and predicted, or difference for these sections here with a higher prediction. Yeah, that was the opposite. But once you have selected this, you could also go with the global coefficients. You can update them, and then you've basically download your verification data, your optimization data, validation, and then your coefficients in the XML. That's kind of the process to go through. I do have a few let's see. I have some additional examples of the kind of show what I did for the rutting. Why is that occurring? Is that an issue with the base, the subgrade? Is it a because is it an AC related issue? You kind of see here with the coarse grain versus fine grained, and kind of here with the large bias. It's a very large bias between these sections. Then basically, as your predicted increases, so does the bias. And how do you bring that values, this prediction, back up to the line of equality? And that's how you can adjust some of those. But I believe this is more of a subgrade issue than anything else. And there's kind of sensitivity of the fatigue or the AC rutting models. So you have, as you increase beta, it just shifts the curve up and down. Now BR2 and BR3 adjust how quickly that slope increases and how much rutting you get early on or flatten it out. And it all depends on what your data shows you. Here for BS1, for subgrade, it basically just shifts it up and down. And basically you want to determine which ones you want to change. And it really depends on what your data shows you, as I mentioned. Let's see. Oh. Got timed out. So I did another example here where I removed all the sections that I believe had top-down cracking and basically reduced it to like 9 projects from an optimization standpoint. I ran a couple different combinations, kind of see what those look like. And most of it are down below. Yes, you have a higher standard error. This one had the lowest bias. So you can see these two sections really dictate your design, but all of the hypothesis tests have passed. But I would still go into investigating why and what's different between these different sections. All right, and that's, I think, all the examples I had. I'm sure there's questions, but it's in general, there's a lot of judgment decisions that need to be made when you do the calibration, and really need to focus on the models themselves to guide you in selecting the different coefficients that need to be changed.
All right, thank you, Wouter. There's a few more questions that came in since the last time we answered these. So let's start back off here. And we have about a half hour left, or maybe a little bit longer, like 35 minutes. So if you do have questions, feel free to start typing them in here, and we will get to them as in the order I receive them.
Yeah, and I noticed that Harold has responded to some of them.
And Harold has been responding, so some of these have already been taken care of. I think the one, okay, so here's the first one we have here, Wouter or Harold, either of you feel free to answer. It comes back to the IRI, the IRI question. There's some more clarification here. The output of the cat is a CSV. Is that correct? In other words, can we use the output of the cat for other distresses in here for IRI?
the output of the CAD is just the measured and predicted data, right? So let me. I had that folder open. Yeah, 1 second. So that the output is an XM for the coefficients themselves is an XML. So that is not CSV. The actual verification and calibration data that is downloaded. So if I go, let's see. So if I download my optimization data, it just gives you your project ID, your measure data, and for IRI, it uses the same sections. It just needs to also use the calibration coefficients that were derived for rutting, fatigue cracking, thermal cracking, and so on. Otherwise, if you have not made any changes, those will still be the global values, and then you can adjust the IRI specifically. So, I mean, there's no way to, all of this, the measured data for rutting and all that is tied to when you do a running calibration, but the predicted values for the IRI are going to be predicted for all those sections. And that's where the previous calibration coefficients, say for a rutting model, will help with your IRI. Because IRI is independent of all those, but it is a function of all the other different distress models.
All right, so let me get back to my spot here. Harold's answering some of these for us, and Chad's answering some, so we're moving along. What is the difference between when we run calibration by changing C1 and then C2, and when we run calibration by changing C1 and C2 simultaneously?
Well, it's so for C1 and C2, if you just change them at the same time, it's going to look at what you've entered. So it's still going to run all the different combinations of C1 and C2 to find and basically see what the results are for each one. So I think this one, we're at 36 runs, well, 756 runs. I changed both C1 and C2. So I changed C1 from 0.2 to 1 in 6 increments. So that's basically it'll take 1 minus 0.2 divided by 5 to give you your increments for each one, and then you decide on which one is best based on your predicted data. And kind of what I showed, where's that presentation? I mean, mathematically it's pretty much the same, except I wanted to first see, where is it? Wait, where'd it go? This. And here, and I base my decisions for C1 will shift where you start increasing your predicted cracking in the transfer function. So that's why I chose C1 first, because the global model here is this kind of red line. So you can see I needed to shift this basically needed to shift the curve to the left because that's where most of my measure data is. Now, if you change your damage coefficients, it'll shift all these points to the right. So that's another option. But what you introduce then is that you might be increasing or predicting too much damage for the typical sections. And why I'm saying I did not want to do that in this case, because I went back and looked at most of the cores, and most of these are top-down cracking, and you don't want to basically introduce a significant bias or skewed results by calibrating to sections that are all top-down cracking instead of bottom-up. And that's where knowing what your data is showing is so important, and doing some investigation, at least at cracks, to see if it's top-down or bottom-up. because you don't expect a very thick section here. So you can see here, this is a thick section with a lot of damage and a lot of distress. So, or very little damage and a lot of distress. So that's why I went back and looked at the course to see if it was a top-down cracking. Harold, feel free to, if I missed anything there. I know it's kind of a while ago was the question.
And there's a follow-up to that, actually, Wooderson. I think the question now is regarding the C1 and C2. We run simultaneously. Is there any interactions, same results when running a sequence, or run at the same time?
I mean, I'm sure different combinations could give you similar results, but yeah, I'm not really sure because one affects the slope versus the other affects kind of the initiation, and if you need to kind of look at the transfer function itself, but they affect different parts of the equation. But I mean, if you run C1, if you change that to 0.2 all the way through, and then you decide to change C2, your C1 stays the same. I mean, it's going to adjust the slope of this transfer function curve, right?
All right, here's a different question for you, Wooder. How frequently do you recommend to do the recalibration or update the calibration coefficient?
That kind of depends on what data you have available, and also if the models have changed. If you have additional data available, so say you have 10 more years of distress data, that becomes an important time to at least run the verification. And verification could be run basically at any time, but to avoid a lot of resources to go that way, I think we've kind of suggested 5 years to kind of at least look at the initial verification based on your older coefficients to see if anything has changed. And then you make a decision if you do need to. If there's no significant difference, then you don't need to recalibrate. Yeah, and I think Harold also added basically the initial calibration suggested a period of about 5 years. That's just general guidelines, and it also depends on whether you have had something change in your construction specifications. Yeah.
Yeah, so if I skipped over your question, you didn't hear it read out loud, just take a look in the Q&A box. Harold is answering some of these as we go to help save on some time here. I have two more that haven't been answered, so we'll jump into these two, and then that should be everything I have at this point. The one question is, will the CAT display the best fit lines for your data?
It does not currently, but it can as I think that's a good feature to add. I don't know, we have a list of other features we'd like to add as well. One of them is like the SE over SY, kind of give you an overall model indication from your different fits, which kind of ties in with that best fit line that was mentioned.
Yes, Scott, that's a great suggestion. I think what we're going to do is we'll document that suggestion for a best fit line, and we'll take it to the task force because we're preparing for everything we want to do for fiscal year 22, and we'll make sure maybe some of those get added in for enhancements we provide for FY22. Thank you for that. And the last one I have here is, could you show the JPCP calibration options again?
Sure. So I'll just start a new one. Yeah, so there was something we fixed last week where some of them weren't updating or weren't showing, and that was fixed. JPCP. Let's do. I don't have any JPCP projects on here as owned, and since the rigid recalibration has been done, there's also very I don't think there's any LTP projects either. But I can show you the options. We'll start with V26. We'll select those, but see now you have new JPCP, new CRCP, and you have your IRI, transfer cracking, and faulting. And then it's basically similar. You have PCC thicknesses, your soil types, mean air temperature similar, some edge support if you have widened or non-widened lanes, some of the base type items like stabilized base, AC base, which is granular, and then your joint spacing to also separate out, and then load transfer doweled versus non-doweled. Does that answer your question, Justin? Hopefully.
That is all the questions that I seen. Justin says yes. You've answered that.
Okay.
I got what he needed. So I'd say maybe give it another minute or two if anything else comes in.
Okay. Vuder, this is Harold and Ryan. Just can you hear me first?
Yep.
Oh, good. On the one thing I'd like to, you already answered it, Vuder, but the combination using single parameters by themselves versus using multiple parameters by themselves. If you use the same ranges, both by themselves as well as the combined values, you have the same range of all the parameters, I would expect the results should be very close. The one thing you have to be careful with, though, is when you get in narrowing down the range of one of the coefficients and you're using multiple ranges, it's kind of like some of the back calculation programs. You got to be careful that you don't get caught in a minimum reduction that's not minimum standard error versus the overall lower standard error. So you got to watch for these localized minimums that can occur.
All right. It looks like there's another one just came in, a question here. It says we have already local calibrated the IRI. So if we perform local calibrations for top-down cracking, questions came in, something moved on me. If we perform local calibration for top-down cracking, do you recommend we recalibrate the IRI?
And top-down cracking is incorporated in the IRI equation, but it's combined with the bottom-up, so it's like total lane area or total area cracking. I mean, I would see first if there's a difference. I would run the initial verification just to see, and then decide.
I would concur with that because they're both included, regardless, and if you've calibrated for bottom up, the program is predicting top down, and that is still being used in the IRI. So after you've calibrated top down, you're going to have the predictions, and I would just do a validation. And if there's a big difference in the IRI, then you should recalibrate. A significant, I shouldn't say big. If there's a statistical difference, then you should recalibrate. If the statistical difference is nil, or there's no statistical difference, then I wouldn't recalibrate.
do think we have another poll question. Let me go to that.
Yeah, voter, did you want me to launch that now?
Yeah, let's do that.
The poll should be open.
Yeah, it should be pretty short one. And I think I missed a word in the question.
Victor, I'd like to come back to one of the questions that was in an answer
Okay.
before we get through.
Yeah, once the poll closes.
All right, we'll give it about another 10 seconds here. Okay, that closed it up.
Okay. Go ahead, Harold.
Yeah, there was it's an answer, but it's a question, and I don't know if you already covered this, and it's noted if the field cores are showing delamination between AC layers, do you have to eliminate that section, or do we have to change the friction values in pavement ME? Did you answer that one?
Not directly, but I did have a slide on that, but that's how some of the sections have been characterized, basically change the friction value.
Yeah, I want to emphasize that delamination would be considered an anomaly, and I would kind of strongly advise that when you do your calibration, you generally don't want to use sections that are anomalous or have a significant anomaly in the observed result. And if you know you have sections that have debonding or delamination, I would put those to the side, not include those in your initial calibration. And what they would be used for is kind of a check on just the debonding simulation in the pavement ME, both the simulation as well as the magnitude of the friction reduction in pavement ME. And the friction reduction, as most will know, once you start decreasing the friction, you go from like full friction to no friction in a very small window of the friction loss or friction value. So it's really either a yes or a no. You either have friction or you don't through the elastic layer program. And so I would be careful about including anomalous sections in your local calibration to establish those local calibration factors. You got to be very careful about that.
right, looks like we have one more that came through here. Harold would or whoever would like. It says our performance data is collected based on long CR for TD and
Longitudinal cracking for top down.
yes, and
Alligator
No,
cracking
I-
for bottom up.
all right, you got this. So we also did not have cores to look at. How can we use the output of ME 2.6 for BU and top-down cracking? In other words, is there overlap between bottom-up and top-down cracking output in 2.6?
So both bottom up and top down are treated separately as part of payment ME, and then it gets both get combined when looking at IRI. There is a procedure that we use to determine if it's bottom up or top down as an estimate based on the damage value and the measured data. And that was implemented for when we looked at the top down cracking model.
Okay, Vooter?
Yeah.
On that top-down, bottom-up, very good question that different many agencies are going to come up to and have to address. To put it kind of simply, I don't know that we have a very good answer, with the exception, as Vooter mentioned, there is a recommended procedure that's based on damage versus cracking that is included in the top-down cracking addendum that is available. And that's separating them out to do the individual, the calibration for the individual cracking, top-down versus bottom-up. But whether they're considered in terms of overall cracking measured values, each separately or combined together at the end, that's something that probably needs to be looked at. In the original research report, they were considered totally separate, which is what we implemented. In reality, that may or may not be the case. And I hope the participants understand kind of what I'm saying there. So the research study considered them, that was one of the assumptions or items going in, that they were totally separate. But is that reality? And when we implemented the NCHRP top-down cracking, we stayed with the assumption originally used from the NCHRP project. But whether that is a correct assumption, I don't know that we clearly know the answer to that question yet. That may muddy the water, but I thought I had to say that.
Is there a place to access the procedure?
What do you mean, is there a place to access the procedure?
I guess the question is,
Basically,
Where-
the report. Yeah.
yeah, I guess it's the report.
The addendum.
Yeah, there's the NCHRP report, and then there is the addendum in AASHTOWare for the top-down cracking, which that is not in the current manual of practice that's published by AASHTO. In the next iteration, it will be.
But the addendum is on the ME Design website.
Correct.
Then we have another question, but it's not necessarily related to the calibration. Let's see, do we need to download both Mira and NAR database to run ME software properly? You need to download the climate files that you want to use onto your machine, yes. You don't have to download the entire database, and Mira is obtained through the LTPP InfoPave climate tool, and then NAR is available on the ME Design website where you can download it for your specific agency. You can download all of them if that's what you would like, but Mira is basically on its own. Basically you download a single one at a time. Okay. And all the addendums are on the ME Design website under documents, and there's webinars as well. So all of that information's on the documents folder within the site. We can check that it's there, but I mean, it's really easy to access. Okay. All right, I don't see any more questions right now, Ryan. I think probably.
Yeah, I think we can wrap up. So I guess I'll start off by thanking everyone for today. I really appreciate everyone who attended, and we appreciate all the questions. It definitely makes webinars more interesting when people are engaged, like everyone here was. So thank you for being engaged. Thank you for asking all the questions. From the AASHTOW end, if you have any questions, concerns, issues with the software, or need a follow-up discussion, my email address and phone numbers on the screen right now in the top left of that slide. So please do not hesitate to contact me with anything. And I may not be able to answer your question, but I'll be able to get you in touch with someone who will be able to. Additionally, Clark Morrison, he's the chair. He wasn't able to join us today, unfortunately, but he is the chair of the task force for the Pavement ME Design software here at AASHTOWare. So if you want to speak to him or have questions for him, please shoot him an email. I'm sure he'll be happy to answer your questions that you might have regarding the task force and decisions the task force makes, or get me involved or someone from ARA if needed. Also, I think there's a contact for the user group on here, so I'll make a quick pitch for the user group. If you're not involved with the user group, please join it. Doesn't really cost anything to join the user group. You're more than welcome. You'll be included in some emails. And really the user group just allows the task force and AASHTOW to basically hear what you like, what you don't like, what issues you have, and we can get that information to the proper people to make those changes, as well as some great training goes on every year there. So if you're not part of the user group, which I'm sure many of you are, please join that user group. You can reach out to me. You can reach out to Christopher at Federal Highways. Either of us can help you out.
And we'll also be updating because I think Chris is stepping down.
Yes.
Jennifer's taking over. So we'll update these as well to make sure we have the most updated. But that's to come probably for the next webinar. Okay, that's all I had.
So if there's nothing else, thank you, everyone. Have a great rest of your week and a great holiday. Talk to everyone later.
Thanks, everyone.